The operational transconductance amplifier, which is great because it sounds like something out of Star Trek, OTA for short, and the operational amplifier, the op-amp. These devices really are so similar they're practically cousins, which shouldn't be surprising considering the similarity of their names. So why is the op-amp so popular? An order of magnitude more popular. You find op-amp literature everywhere, tutorials and circuits, and it's just in everything everywhere. And the OTA really isn't. The OTA is a really good chip, as I have learned. My first video that got spread to a whole lot of people, hello audiophiles, the 555 timer intro video, a couple people suggested that I check out the OTA because it has audio uses, and it does. And the information about the OTA is there, data sheets and tutorials and stuff, but it's just not that common. It took me nearly 10 minutes of Googling alone just to find any website telling me why I should even care about this chip. It didn't take that long to figure out how it worked, but it took me a while to find anyone anywhere talking about why I should even use it. So there's two reasons for its unpopularity. The first is that it's a little less intuitive. For an op-amp, it's dirt simple. Voltage in times the gain equals voltage out. This is your op-amp equation, and this is the differential input. Both of these are the same. They have a differential input, a non-inverting and an inverting, so non-inverting minus inverting equals the differential input. Both the op-amp and the OTA work that way. So the OTA equation is quite similar. Voltage in times transconductance, there's that word, equals current out. In a conceptual sense, it turns voltage into current instead of voltage into voltage. So it's a little less intuitive, and it takes more work to configure this chip. You can't just throw the circuit together with a couple resistors or even no resistors. So the op-amp is easy, the op-amp works, so more people use it. And the rich become richer, so the popular op-amp becomes more popular because more people are working with it. And the other reason is the OTA is really good at what it does. It's a superb chip for what it does. But what it does is much less useful nowadays. The OTA is fundamentally an analog signal processing chip, including audio, is an analog signal. And we just do a whole lot less analog signal processing. Digital signal processing has become easier, cheaper, more readily available, and most importantly, high resolution, good accuracy and precision. If you have a magnetic storage medium like a cassette tape, like high quality studio tape, the analog signal resolution is an atom. That's the granularity, is a single atom. No digital system currently available on Earth will be able to replicate that. The amount of data are just immense to even think about storing that much information. But we don't need to, because after a certain point, it doesn't matter. Now, there are still people that do audio processing with analog hardware for fun. They just like doing it that way. And there's also high precision industrial, military, laboratory science situations where you actually need that extra precision, working in gigahertz, terahertz, or even higher frequencies, working with voltages that are minuscule, working with, your Intel CPUs have transistors that are atoms big. So there are certainly situations where you still need analog processing, but you just really, most of the time, don't anymore. So they're just not that needed. But they're still really good, and they have been getting better over time. I'm using the LM13700 chip and the Texas Instruments datasheet for it. This is, from what I can see, the absolute best OTA available on the market for both low and medium tier. There's better ones for scientific applications, the really, really high quality ones, but these aren't cheap. From Mouser, I got 4 of these. It was $2 a chip. If you get, 10,000, they're going to be cheaper, but $2 a chip is not really that cheap, but they're really good. And the 13700 apparently is specifically designed for better audio processing fidelity. So there you go. So now that we know that the OTA is great, in the limited circumstances it's still needed, let's talk about what it is. What in the Sam Hill is transconductance? So here's the thing. There are 4 types of amplifier: voltage, transconductance, transresistance, and current. Another name for these is a voltage-controlled voltage source, a voltage-controlled current source, a current-controlled voltage source, and a current-controlled current source. You might notice that this is a grid. So on one axis, we have whether voltage or current controlled, and the other axis we have whether voltage or current source. Now, those of you who are astute and understand the physics here will realize that this is nonsense because there's no such thing as turning voltage into current or turning current into voltage. Current exists because of voltage. You apply voltage to a wire, there's stuff on the wire, in a circle, current flows. Voltage causes current. That's it. End of story. Voltage causes current. This is conceptual. Don't get hung up on it. It's like we look at a BJT, a nice NPN transistor. We say the NPN transistor is current controlled. No, it's not. It's actually not at all. But conceptually it is, because if we think of it as a current controlled device, if we do our math based on a current controlled device, it's easy to work with a BJT. That's why we do it. So conceptually, you have voltage or current input and voltage or current output, and that's your 4 different types of signal amplifiers. Don't get hung up on the physics, just think about it conceptually. Your op amp, your regular op amp, is a voltage-controlled voltage source. Now, what does it mean to have voltage or current in? That one's easy. You have a differential input, these two voltages subtracted from each other, but you have a voltage applied to a pin, just like every other IC in the world, and the internal circuitry does something with that voltage. That's voltage in. Current in is just the same as your multimeter. Think of it as a multimeter. Think of the chip as having a multimeter. You can measure voltage, you can measure current with a multimeter. So that's the easy part. It's just whether it's using voltage or current as input. What about the output? Voltage source, a voltage output. Remember, there's a load. We have a load and we have a signal source, and we connect the two together. The load can be an actual resistance or it can be an effective resistance, like a speaker might have a 6, 8, 12, 36 ohm impedance. So in any case, you apply a voltage, you have a resistance, and you get a current. What does it mean to have voltage in, voltage out? It means there is a certain voltage applied across this load. This load has a certain voltage drop. That voltage is proportional to the input voltage. Voltage out, voltage in means whatever the voltage for the load is, it's proportional to the voltage in. So if you have, let's say you have a potentiometer, a variable resistor, and you hook it up to an op amp, you're going to have a certain voltage across that variable resistor. If you change the value of that resistor, if you turn it up and down, the voltage across it will not change. V equals I times R, Ohm's law. If R goes up, I goes down to keep the same V. So the current is changing, the voltage is not, so it's a voltage source. That's the conceptual thing. You don't think of voltage or current as an output as in here's current on a plate, here's some current. It's that the output applies a voltage across the load proportional to the voltage in. So the OTA, which is a voltage-controlled current source, across the load there will be a certain current proportional to the input voltage. If you change the value of this potentiometer, then the voltage across the load will change because the current is not. V equals I times R. If you change R and you don't change I, then V is changing. So the output current is proportional to the input voltage. That's what output and input mean. So that's all transconductance is. It's just a fancy term to say the load is going to receive a certain current proportional to input voltage, instead of a certain voltage proportional to the input voltage. For an op amp, if you change the load, the voltage does not change. For an OTA, if you change the load, the current does not change. Now, if any of you have looked up OTAs before, you will notice that the circuit symbol I'm using is a little different. There are probably a dozen different symbols for OTAs over the history of their development, but in modern times, you're pretty much going to see this one. You have your normal triangle, and you've got your plus and your minus. It's 3 inputs. You've got your 2 circles that are supposed to overlap, and then down here and down here, and then you've got 2 diodes, and they look sort of like this, whereas this is the symbol I'm using, which is very similar to the op amp on purpose. The reason I have not bothered with this is it's not part of the OTA. This is something called linearizing diodes, which don't have to be there. They are nowadays because technology has advanced. But these are called linearizing diodes, and they are there only to make the OTA behave more linearly, hence the name. They just make it work better. They're not an input. They don't affect the output other than making it more correct. So it's not useful to constantly have it there. All you're going to do is hook up some voltage to it across a resistor to give it an input current, and there you go. And it's just like, oh, power your chip. It's the same reason, like, we don't draw positive and negative power on here. We get it. You power the chip. Put your VCC here, put your ground here. We don't need to say that every time. So the same thing here. This is just something you hook up, and it's not part of the operation at all. It's just there to make it better. So we're not going to worry about that. I will discuss it in a minute, but just don't worry about it for now. So what are the inputs of this OTA? How does it work? So the op amp takes a differential input voltage, and you usually use it in closed loop formation or a closed loop configuration. That means the output feeds back into the input, and you configure it with resistors optionally. And what happens is the chip, the feedback, causes the differential input to go near to zero, just a hair above or below zero. So the differential input ends up being millivolts, just a handful of millivolts. And the crazy gain, 100,000 or more, causes this big ol' voltage output. The OTA is generally not operated. It can be operated in closed loop form, but it's generally not operated in closed loop form. It's generally open loop because this third input, which is commonly called IABC or I bias, other things. ABC is amplifier bias current, if I recall correctly. It doesn't matter. You'll see it. This input directly sets the gain. For the op amp, you use feedback and configure the gain using your resistor, voltage divider, whatever. And it automatically sets the inputs to be very near zero. That's how it works. The OTA does not. You can supply whatever voltages here you want, but if they are not close to zero, if the differential input is not close to zero, the inputs can be whatever, but if the differential input is not close to zero, then it doesn't work right. That's the thing. The op amp automatically does this for you. Here, you have to set up a big old voltage divider or something, but the inputs you have to manually set to be 10 to 40 millivolts apart. If you're using those linearizing diodes, then you can go up to maybe 80 millivolts, but like 80 millivolts is already getting like 1% signal distortion. And if you try to go up to a single tenth of a volt, you're losing maybe 10% of your signal. That has to be small. And this is another reason the OTA is a little less popular, because you have to do that yourself instead of having the chip do it for you. But basically, you set your differential voltage and then you apply a current here, not a voltage, a current. And the current in this IABC or I bias sets what's called the transconductance. Remember a minute ago. Voltage in times transconductance, I don't remember why it's GM, don't worry about it, equals current out. You're applying a current here, I in, and this is your V in, which is V plus minus V minus. It's the differential. So your V in is going to be 10 to 40 to 80 millivolts, positive or negative, if you're giving it a negative supply. Your transconductance is a unit in what are called Siemens, or 1/Siemens, I forget, but it's just, we have amps per volt. Siemens is either amps per volt or volts per amp, I forget which, but we don't need to know any of that. This is not a physics course. We can learn about Siemens later. Transconductance is your gain, and it's set by this current. You turn the current up and down into this pin, and that turns your transconductance up and down, which turns your output current up and down. And we've discussed it's a current source. That's what these two little circles are. Two little circles, wherever you see it, is a constant current source. It means the voltage varies to keep the current constant. So I'll go into detail on that in a moment, but I want to mention one thing. Now that I've mentioned the output, OTA plus buffer equals op amp. This is an equation. Now, obviously, you run them different ways because the op amp, you use feedback, and the OTA, you use this IABC or whatever. But fundamentally, if you add a buffer to an OTA, it behaves like an op amp. Now, why is that? What is a buffer? Let's say that you have your signal source and you have your load connected together. Your signal is the voltage. The varying current is not a signal. The voltage is the signal. If you have a voltage source, if you take this load and you change the load, if you change the amount of the load, you're going to get the same voltage source. So you can do whatever you want. You can hook this up to a microcontroller pin. You can hook this up to a speaker, assuming your chip is capable of this. You put a power transistor if you need to. But ignoring power requirements, the idea is you can hook up a high impedance, a low impedance, whatever load you want, and the voltage, the signal will stay the same, and it will feed the load properly if it's buffered. If it's not, then it won't. This is not a constant voltage source, this is a constant current source. If you do not change the input voltage, if you do not change the configuration, if all you do is change the load resistance or impedance, your voltage, your signal will change. Because if you've got 1 amp and you've got 1 ohm, you get 1 volt. If you've got 1 amp and 2 ohms, you've got 2 volts. If you have a constant current source and you increase the resistance, it's going to increase the voltage output. This is going to output a higher voltage to cause the same current. If you reduce the load, it's going to output a smaller voltage to cause the same current to go across the load, constant current source. So this is unbuffered, because if you hook it up to a microcontroller pin, if you hook it up to a speaker, you're going to get different signals. And you may have heard of loading the output of a chip or something. If the signal generator, like this is an issue. Remember, I showed you in the previous video where I plugged in my oscilloscope probe and it messed up the signal? I was loading the signal generator. If you have a high power load, low impedance, and you hook it up to a signal generator, that alone can distort the signal because it'll mess with the internal components here. You know, you get parallel capacitance, parallel resistance, it messes with voltage drops of BJTs or whatever. So that's another reason to use a buffer, is so that you don't mess up your signal with a load. So it's the same principle. So that's why the OTA is called unbuffered, and if you add a buffer, then it becomes a voltage source, because if you add a buffer, then the impedance is going to be the same every time. It's going to be a high impedance input to the buffer. So whether you hook up a speaker or a microcontroller pin or whatever, the input of the buffer is going to have the same impedance, so it'll be the same signal every time, because same impedance, same current equals same voltage, and then it doesn't matter how much power is drawn through the buffer because it's using the same input voltage. So that's why a buffer turns an OTA into an op-amp, other than how you set the gain. So that's another thing about the constant current source, is your load matters. So let me draw a full example of this chip. The 13700 chip has 2 of them in there, but let's pretend it has 1. So inside we have our output. These are supposed to overlap again. We have our bias, we have our plus, we have our minus, we have our, I'll just draw the diodes like this. That's good enough. We have our diode bias. And then of course we have our V plus and V minus. And these are the pins that are exposed to the chip, or from the chip. All these pins. So up here, you have your positive power and your negative power, unsurprisingly. And then you have your 2 signals. Here, I'll put the little power up here so we can see it. So here's our dual power supply. We've got positive voltage, negative voltage, and the circuit ground in between. So we have 2 signals relative to circuit ground, of course. Let's call this signal A, and we'll call this signal B. So you put one signal into the non-inverting, the other signal into the inverting. Now recall that these have to be only, 10 to 20 to 40 to 80 millivolts apart, millivolts. So you may need to do a voltage divider. You probably will. Like if you have an audio signal, it might be 1 volt peak to peak. So just put the signal through a regular resistor-based voltage divider and hook that in here. And of course, you could also have B connected to ground instead, so you have a signal reference to ground. And this is just if you're trying to amplify one signal, then it's just relative to ground, so the differential voltage is that, and then you just have a voltage divider there. But however you hook up your signal, you just have it be not too big, and then over here is your gain control. So very simply, let's say you have a physical knob. If you have positive into a potentiometer and negative, not ground, negative, then here the wiper would be your input, but I forgot the resistor. So a voltage divider through a resistor into here. If you're using a microcontroller or whatever, some sort of varying voltage programmatically, then instead of this potentiometer, you just put the voltage through the resistor. But if you're using a physical knob, you'd use a voltage divider like this. And how big is this resistor? Look on your data sheet. My data sheet recommends that the maximum current going into here is 1 milliamp. So you have your positive and negative. Let's say that positive is 9 volts and negative, so positive is 9 volts and negative is negative 9 volts. So altogether that would be 18 volts. So 18 volts divided by 1 milliamp equals the resistor you should use, so that when you're all the way up at 9 volts, then it's going to put through that much current. Now in my data sheet, it says that the spot here is 2 diode drops. When somebody says a diode drop, they mean like base to emitter junction drop or a regular diode drop, 0.6, 0.7 volts. That's just the standard industry figure, 0.6, 0.7 volts. So anytime you see a VBE or diode drop, it just means 0.6, 0.7 volts. So actually it would be 18 minus 1.4, because 0.7 times 2, if it's 2 diode drops above the negative voltage. Just look at your data sheet. So you could actually say this is 16.6 volts, perhaps, over 1 milliamp gives you your resistor. So the biggest gain you will have is when the voltage is as high as possible, it's all the way up at positive, you'll get 1 milliamp, which is the recommended maximum. The actual maximum is 2 milliamps according to my data sheet, but you shouldn't intentionally run up against the absolute maximum ratings. 1 milliamp is recommended, it's plenty. So at 9 volts, it'll be giving 1 milliamp. At -9 or -7.6 or whatever the voltage here is, if the voltage is the same, it'll be getting 0 milliamps. So it'll go from 0 to 1 milliamp as you adjust either the potentiometer or whatever voltage input you have. So that's how you pick this resistor. It's just that. Then you have your output. There's your output. You know what to do with an output. The final pin is the linearizing diode. If you don't hook up the linearizing diode at all, the chip will work fine. It just won't work as well. So here's the thing. The bigger the differential voltage, not the individual voltage. The individual voltages don't matter. The differential, once they're subtracted, the bigger that value is, the less the response is linear. It'll still go up, but it won't go up like 1, 2, 3, 4 in, 1, 2, 3, 4 out. It might become exponential, logarithmic, whatever it does. So your signal will get distorted, basically. So let's say you have a quiet portion, which, like if this is relative to ground, and your signal is in a quiet portion, then this is going to be closer to 0, because A is not varying much from ground, it's quiet. So you're going to get a correct value. But the louder your signal gets, the higher the amplitude, the bigger this differential voltage. So the louder it gets, the more distorted it's going to get. So it's going to get too loud. And if you have, high and mid and high and mid, and your waveform is wiggling, that might sound great normally, but if you don't have a linear response, then everything is going to get warbly. So that's why you use your voltage divider. So basically, if you have ground or B or whatever, in order to decide how to divide the voltage, you just have to say, what is the biggest input voltage I'll have? Difference. What's the biggest difference? So 1 volt peak to peak. So that would be plus 0.5 volts minus 0.5 volts. So you have to say, okay, the actual difference is going to be positive or negative 0.5 volts. So I have to use a voltage divider so that the loudest the signal will get, so let's say 0.5 volts, let's say it can't go above that. So 0.5 volts, bring that down to 40 millivolts, 80 millivolts if you're brave, and you're using these diodes, but just a few millivolts, and then it'll be fewer millivolts if it gets quieter. So you set based on the maximum. So set a voltage divider that's going to bring your ground or B or whatever, so that the difference is never more than however many millivolts based on your input signal. And that's how you decide that resistor. So the linearizing diode just makes it behave better if you have a bigger difference in voltage. Now, why wouldn't you just always use the smallest one possible? Because of noise. The smaller you make your signal with a voltage divider, the more susceptible it is to just noise in the circuit. And you can armor against that. You can put your bypass capacitors across your power to make sure there's no power supply ripple, and use all kinds of shielding, and there's a billion different ways that you can reduce noise, but there's still noise. So it's nice to be able to have the voltage be a little bigger and do all those anti-noise mechanisms to just get the absolute highest quality signal. But if you don't care about noise, if you don't care about distortion, or whatever, you don't even need to hook up the diodes. Just don't worry about it. Maybe hook them up to a capacitor to ground or something. But I would just, you could just leave it, if you don't care about noise, just leave it floating, it doesn't matter. But what if you want to use it? You apply positive voltage through a resistor, and you just leave it there. This is not something that changes, it never changes. You put it on there, and you leave it on there. This is another reason why I don't bother having these diodes here. It's just like positive positive and negative power. You just hook it up and you leave it. It's not part of using the chip. The data sheet that I have also recommends 1 milliamp for this. Remember, this is a current in. Just like this diode thing, it's based on the current, not the voltage. It doesn't care about the voltage. So the data sheet says you should have about 1 milliamp coming in here, and it can go up to 2 milliamps. It also says the current coming in on the diodes should be at least double the current coming in on the inputs. Now, this is a little unclear in the data sheet, but I have intuited from the data sheet that 1 milliamp to maybe 1.3 milliamps is pretty good. It says that the voltage at this pin is going to be 1 diode drop above circuit ground. Now, there is no circuit ground input here. This chip doesn't know what circuit ground is. So I'm assuming that it's just between positive and negative, it's halfway. Because you're usually going to have like 9 volts and minus 9 volts, so it'll divide evenly into 0. I imagine that if you had 9 volts and 5 volts, then this wouldn't be 0. But you're probably going to have plus and minus the same value. But that's what the datasheet says. The datasheet says 0 volts, but they're assuming that you're going to have, positive and negative the same number. There's no, this chip has absolutely no way to know what circuit ground is. So just hook it up this way, and it says a diode drop above 0, so about 0.7 volts. So positive minus 0.7 is the voltage, and then you have your current. So let's say you want 9 volts, so let's say that's 8.3 volts divided by, let's say 1.3 milliamps, and once again, that's your resistor. The absolute maximum rating is 2 milliamps, so 1.3 isn't going to hurt it. So you just decide on your resistor value, hook it up, and leave it alone. And as usual, it's taken me forever to explain this, but I'm going into extreme detail so it's completely clear. So now time for a very quick summary. Your positive and negative differential inputs, your non-inverting and your inverting inputs, are the same as an op-amp. It's non-inverting minus inverting is the differential input. Your op-amp will automatically make the differential input very close to 0. 10, 20, 40, 80 millivolts. For the OTA, it does not. You have to do that yourself with the voltage divider, so make sure A minus B or A minus ground is never higher than however many millivolts you decide. Use a voltage divider on A or A and B. Your linearizing diode input can be left open if you don't care about noise or distortion. If you do, then look on your datasheet and see what the datasheet recommends. Mine recommends, I'm using the TI datasheet, Texas Instruments, and 1 to 1.3 milliamps seems to be right. So your positive voltage, that many milliamps, gives you this resistor, hook it up and leave it. Positive and negative power. And you can use it single supply, but why? Single supply op-amps are much more useful. You're doing logic and comparators and other things. I'm sure I will eventually come across a useful single supply OTA, but we're processing audio signals, which you should be doing with positive and negative voltage, so there's no DC bias. So let's just assume you're using negative power. So positive and negative power, just like so. Make sure they're the same value, plus or minus 9, plus or minus 12, plus or minus 15, whatever, so that this thing knows, gets the right 0. And then this is your transconductance. It's just a current, more amplification, less current, less amplification. So this recommends a peak of 1 milliamp. So your voltage divider or your voltage input, when it's the highest, should be giving 1 milliamp, and then when it goes down, it'll be giving less, and that's all there is to it. So what about the output? And of course, you can see this is more complex than an op-amp, so this is why it's less popular, but how do we use the output? What do we do with the output? It's a current. What do we do with the current? You put a load across it. So let me take all this down. So you know how I said if you add a buffer to an OTA, you get an op-amp. As it happens, there are buffers right on the chip. The 13700 has a buffer right on the chip. So it's clearly intended to be used that way, although you don't have to. You don't have to hook up the buffer. But this is how you work the chip. Here's your OTA. Here's the output. You give it a load resistor, which you connect down to circuit ground, and that's how you do the output. What you're going to get here is a voltage. Your input differential voltage multiplied by your transconductance, which is just the current here, up or down, will result in a certain current across this resistor. More current, more voltage, less current, less voltage. So this resistor is going to have a varying voltage drop, which means this spot is going to have a varying voltage, and that is your signal. Now the reason for the buffer is to make sure that this load value doesn't affect the signal. You could perhaps plug this directly into a chip. If that's just a microcontroller with an analog input pin, you might be able to just hook this up and read this signal if you wanted to do some audio processing analog style and then read the final result digitally. But not every microcontroller, not every ADC works the same way, and they might load the output. Because if whatever resistance this has, whatever effective resistance, it might be constant, it might not be. So if this is changing, you've got a parallel resistance here, which is changing the resistance overall, which is changing the signal, the voltage, because it's always going to try and put out the same current no matter what the resistance changes to be. It's going to try and put out the same current. So if your impedance is changing at all, whatever's reading this voltage, if that's changing at all, then your signal is going to get distorted. So what you do is you buffer it. And there's a million different ways to buffer it, but this is the way Texas Instruments buffers it. It's called a voltage follower. So let's say you have two BJTs. Like I said, these are on the chip. There's just buffer pins on the chip. So connect positive here, positive here. So here's your output voltage. You connect that to the base. The emitter of the first one connects to the base of the second one. The emitter of the second one connects over here through another resistor to circuit ground. And this is your out. This is your buffered output. This is called a voltage follower because this follows, the voltage here follows the voltage here, basically. So this resistor with these bases will have a roughly constant effective resistance because your base to emitter is going to have about a constant voltage drop and whatnot. So you don't really think of the bases of the transistors as having a varying impedance. It's there, but it's the same. And then this is constant resistor, this is a constant resistor. So everything is either constant or effectively constant. So your impedance really isn't changing. Even though there's four of them interacting, it's really not changing. So you end up with a nice stable signal because the impedance is not changing. But the power to drive your load is coming through the collector here and the collector here out into whatever you've got hooked up here. So the impedance that this sees is the resistor through the bases, and here. And this voltage drop goes up and down. This voltage drop goes up and down. Basically, they go up and down together because the input voltage becomes a current. So you've got a current running through here, which biases the bases, and then you get a current here. I'm skipping over some bits. I need to do a video proper on voltage followers, but the trick is basically the current goes through here, you get a voltage, which biases base to emitter, it biases this resistor to the same voltage, so you get whatever current makes the same voltage drop here and here, plus the base to emitter drops. So the voltage here follows the voltage here. This is setting the current, but the impedance doesn't appear to change because whatever varying impedance, whatever power draw you have throughout is fed by the collectors. So that's the buffer, and it's right there on the chip. Now, the datasheet says with the buffer, you still only get 20 milliamps. So you're going to want to put another power buffer after this, unless you're driving something very simple. But that microcontroller pin, for example, that might have varying impedance reading the analog voltage, well, 20 milliamps is more than that would take. So with this buffer, you could plug that in there, and you don't have to worry about whatever capacitance and other nonsense that microcontroller pin is using to read the analog voltage and convert it to a digital value, because that power is being fed by the collectors of the transistors through. The actual load is separate. The OTA is seeing a constant effective impedance, and it's setting the voltage to put a certain current through that effective impedance. And so you get a voltage drop here, which these base to emitter junctions and this follows, and then this gets whatever current it needs to get the same voltage drop over there plus that. I really hope that this video has been clear. I've gone over it in my head a whole bunch of times, and I think that it may just be made more clear as I start to do circuits. Please leave questions down there. I can always do a second video explaining better, maybe explaining more of the nuance of how the chip works. But essentially, you just get your same differential input voltage, and your gain is set by a current, and then you have linearizing diodes, which gets a current, and your output is a current, which you can put across a load and you'll get a varying voltage for the same current, and then you can buffer it to actually use it in something. So let me know if my explanation was terrible. I will endeavor to fix it, but for now, I'll be seeing you.